Good morning, students. The topic today that I would like to discuss with you is the transformation properties of fluxes and forces. Before this discussion, we have already discussed about in some previous classes that how the entropy production takes place when inside a system, particularly when heat change takes place between the different phases of the system, or when a chemical reactions or a series of chemical reaction takes place inside a system, and because of that how the entropy production rate changes. Okay, and now in this particular session we would like to discuss there is a correlation, means when a particular or a particular reaction scheme has been changed from its initial state to final state, means initially the reaction scheme whatever it follows, and in the next step if its reaction scheme has changed, but there should be a correlation between the entropy production rate. So let's have a look of this. So for a chemical reaction, the rate of entropy production is given by, that is sigma equal to dis by dt, that is the internal production of entropy with time. If I divide this thing, I will give the entropy production rate sigma equal to jx. In this equation, the flux, that is J, is identified with the rate, that is V, and the generalized force X is identified with the affinity, that is A by T. Because in this in some previous class we have discussed about that sigma equal to A by T into V, where A by T is the affinity at a particular temperature T and V is the rate of the reaction. So using this equation only. So this is coming from the equation. Okay, so I have written this equation also. So sigma equal to A by T into V. This is this equation have arrived in the next probably the entropy production because of this chemical reaction session. Okay, so now we consider we would like to consider a consecutive reaction. Consecutive reaction means the reactant to product takes place through some definite number of intermediates. So in this simplest scheme, I have assumed a reaction where A to C is produced through the intermediate B. Okay, so in the first step A is converted to B, and in the second step B is again converted to C. So for reaction number 2, the affinity is given by the given by using the relation, because we know that affinity, chemical affinity A equal to minus summation gamma mu gamma into dn gamma, where mu gamma is the chemical potential of the gamma-th species and dn gamma is the change in the number of moles of the gamma-th species. For this particular reaction that is shown in the reaction scheme 2, 1 mole A is converted to 1 mole B, that is the dn gamma is for this particular instant equal to 1 here. So only the A equal to change in the number of moles of B minus A. So A1 for reaction for this particular scheme, A1 equal to minus mu B minus mu A equal to, if I just calculate this thing, so mu A minus mu B will arrive, which is equation number 5. Similarly for reaction number 2, the affinity, that is A2 is given by A2 equal to minus mu C minus mu B. If I just simplify this thing, mu B minus mu C, that is equation number 6. Now the change in the number of moles of A per unit time, we know that change in the number of moles of a particular reactant or product per unit time is basically its rate of the reaction. Okay, so the rate of the reaction of A, that is minus dNA by dt. Here minus sign is used because A is decreases with time, so because of that, so minus dNA by dt equal to V1, rate of the reaction of first this equation. And that is if I simplify this thing, dNA by dt equal to minus of V1, that is equation number 7. And the change in the number of moles of C, that is rate of this second reaction in this particular steps. So dNC by dt, that is equal to V2. Hence the change in the number of moles of B per unit time. So we have from this two scheme we have calculated the change in the number of change in the concentration of A with time and change in the concentration of C with time easily, because this is the reactant, this is the end reactant, this is the starting material, and this is the product. Now we would like to find the intermediate concentration, that means change in the number of moles of B with time, because we know that in the first reaction B is produced and in the second reaction B is decreases. So the change in the concentration of B with time is the resultant effect of both the reaction. Okay, so dNB by dt equal to minus dNA by dt, that is the minus dNA by dt means the rate of the production of B, minus dNC by dt is the rate of the decrease of B. Okay, so this is basically V1 minus V2, and this is equation number 9. Hence, using the concept of rate of entropy production for successive reaction or consecutive reaction, we can say that T into sigma equal to T into dis by dt equal to A1 V1 plus A2 V2, because we have already studied these things in some few class before, because for some coupled reaction or this type of reaction where more than one reaction scheme takes place simultaneously or consecutively, then you can say that the summation of the affinities multiplied by the rate should be greater than or equal to 0, and that should be equal to T into entropy production rate. Okay, so using this concept I am arriving this equation. Okay, now consider now the reaction scheme is a little bit changed, and I have just changed it in this way that A is directly produced to C and another material B also produced to C. Okay, and this is reaction equation number 11 and 12. The corresponding affinities for these schemes are given by, if I now write the affinities for this first scheme is A1 prime equal to minus mu C minus A and product minus reactant, that is chemical potential of the C minus chemical potential of A, and a little bit manipulation E mu A minus mu C. Now if I just compare this equation with the first equation or using the relation of equation number 7 or equation number I think 8. Okay, so if you just remind the equation number 7 and equation number 8, then you will find that A1, where is arrived at A1? Yeah, I found this thing. So equation number 5 and equation number 6, if you remind this thing, we have got for this scheme mu A minus mu C. So if this equation, you can add these two equation number 5 and equation number 6, then you will get mu B cancel out, so mu A minus mu C. That means mu A minus mu C is equal to, you can say, A1 plus A2. So this thing has arrived just. So mu A minus mu C equal to A1 plus A2, and similarly A2 prime, that means the chemical affinity for the second scheme is mu C minus mu B, or mu B minus mu C. Minus of mu C minus mu B, that means mu B minus mu C. And mu B minus mu C is basically A2, just for your convenience, mu B minus mu C equal to A2. Okay. Hence, if I now write the rate of the reaction of this new scheme for the first reaction, that means equation number 11 is minus of dNA by dt equal to V1 prime, and minus of second reaction minus of dNB by dt equal to V2 prime. Then the total change in the concentration of C, that means dNC by dt, because C is produced in both the steps in equation number 11 and equation number 12 both. So I have to add both the rate. So minus of dNA by dt plus minus of dNB by dt equal to V1 prime plus V2 prime. Okay. Now I would like to compare the equation 7 and 8, that is the initial reaction scheme. Equation number 7 is the rate of change of A, that is equation number 7, and equation number 8 is the rate of the change of C. Okay, so if I just compare these two equations with this new reaction scheme, it appears like that minus dNA by dt, that is remains same. That means the rate of change of A is basically same, that is V1 equal to V1 prime, because here minus dNA by dt equal to V1 appeared in the previous equation, and here V1 prime. That means that this is same, so I can write here V1 equal to V1 prime. But for V2, in the previous case, V2 means the dNC by dt, that means total change in the concentration of C, that is was V2, and here we got just few equation before, that is equation number 13, dNC by dt equal to V1 prime plus V2 prime. So compare these two equations, V2 equal to V1 prime plus V2 prime. Hence, the corresponding rate of entropy production is given by, that is T into dis by dt, or T into sigma equal to A1 V1 plus A2 V2, that is for initial equation. And now I just now if I just replace the equation in this way, in place of V1 if I write V1 prime, and in place of V2 if I write V1 prime plus V2 prime, then this total equation comes at A1 into, because at that new condition, in place of V2 you can write V1 prime plus V2 prime, so it will always correlate. Okay, so A1 V1 plus A2 V2. So using the concept of these two equations, so the corresponding rate of entropy production, which is coming out to be T into dis by dt equal to A1 V1 plus A2 V2, for the previous scheme is equal to A1 V1 prime equal to A2 V2 prime. How does it appear? To make it clear, I have just make some calculation. In the previous case, the T into sigma equal to A1 V1 A2 V2 for previous reaction scheme, and for the new reaction scheme, the T into sigma becomes A1 prime into V1 prime plus A2 prime into V2 prime, and we know that A1 prime, which is somewhat here, yes, A1 prime equal to A1 plus A2. So putting converting all these value in terms of the previous reaction scheme, so A1 plus A2 into V1 prime equal to V1, so I have write here directly V1. So A1 into V1 plus A2 into V1, and A2 prime into V2 prime, and we know that A2 prime equal to A2, so I have written here A2, and I have converted this V2 prime in terms of initial reaction scheme. So V2 prime equal to, you can write V2 prime equal to V2 minus V1 prime, so I have write here V2 minus V1 prime. So multiply these things, A2 into V2 minus A2 into V1 prime. Now if I add these two quantities and V1 prime equal to V1, so I have just changed this quantity. So this quantity is cancel out, so it comes out to be A1 V1 plus A2 V2. That's why I have written here, or if the equation comes out to be T into sigma equal to A1 V1 plus A2 V2 equal to A1 V1 prime equal to A2 V2 prime. So notice that the new set of reactions are such that the entropy production is the same. The transformation properties of the fluxes, that is in general we have written in letter J. So Jk for k different fluxes, and the generalized forces for these k different fluxes, that is xk's, are such that we can take a linear combination of the forces to give a new set of forces, that is xk prime, and choose a new set of fluxes, that is jk prime, such that they always follow the relation, that is summation k jk into xk equal to summation k jk prime into xk prime. So this is the transformation properties of generalized fluxes and forces. Okay, thank you.